You know, usually when we talk about picking up a new technical hobby, there is this very predictable honeymoon phase.
Oh, for sure. The beginner's luck period.
Right, exactly. Like, think about your first 6 to 24 months with a 3D printer. You're printing standard PLA, maybe some standard PETG.
Yep.
And you finally have your settings dialed in. The first layers they look glassy.
You feel like an absolute genius.
You totally do. You feel completely confident. You look at your printer like you have just conquered modern manufacturing. But then you decide it is time to level up.
And that is when the trouble starts.
It really is. You actually want to print a phone case out of flexible TPU, or maybe you need a really strong functional bracket out of ABS for your car.
Right.
So you confidently load the filament, you hit print, walk away to get a coffee, and you come back to a complete disaster.
Just a total mess.
Yeah, your extruder is jammed with what looks like, I don't know, aggressive plastic spaghetti. Or the corners of your supposedly flat bracket are curling right off the build plate like a potato chip.
It is a very specific, agonizing type of workshop. Heartbreak, honestly.
It hurts.
It does, because it is the exact moment that illusion of complete control just shatters. We get incredibly comfortable when things are predictable.
Yeah.
When you are printing PLA, all the variables are mostly hidden from you by default slicer profiles that, they just work.
Right, the software is doing the heavy lifting.
Exactly.
Yeah.
The material is forgiving, the thermal dynamics are gentle, and the machine makes you look like a pro. But stepping into engineering materials, the training wheels come off.
And that is exactly our mission for today. Welcome to the deep dive. Today is all about bridging that massive gap.
It is a big gap.
We are talking about the transition from beginner's luck to advanced, consistent results where you are actually in the driver's seat.
Yeah, we are going to build a concrete decision framework for your next workshop upgrade. And we're going to dive into the literal physics of why things fail.
To do that, we are pulling together insights from this really comprehensive spring recap and a fascinating follow-up reader Q&A from printer@3d.cz.
What is fantastic about this particular breakdown is the underlying philosophy it presents for intermediate makers.
Yeah, it is not just a spec sheet.
Right. We are not just going to read off a list of temperature settings. We are covering what we consider the trinity of 3D printing success. So that is materials, slicer workflow, and hardware ecosystems.
And we are going to explain the why behind every failure so you can actually diagnose issues yourself.
Which is so important.
Let's establish right out of the get that we are just two experienced makers comparing notes here. We have both ruined enough expensive filament to know exactly what we are talking about.
Oh, absolutely. So much wasted plastic.
Yeah, and we want to save you from wasting your own time and money. So the first major takeaway, it actually flips standard buying advice completely upside down.
It is a trap so many of us fall into.
It is. You do not buy a printer based on a flashy spec sheet and then try to figure out what it can print. You do the exact opposite.
Right. This is the core of the material first decision framework. It is incredibly common for people to get, intoxicated by hardware specs.
Oh, yeah. The marketing gets you.
It does.
Yeah.
You look at the blistering travel speed or the high-resolution touchscreen, the sleek aluminum enclosure, you just buy the machine.
Yeah.
But you have to define the material based on your actual real-world application first. Let that specific polymer dictate the hardware you purchase.
So if your goal is printing impact-resistant drone bumpers or phone cases, you have to look at flexible materials first.
Exactly.
And that brings us straight to TPU, or thermoplastic polyurethane. Now, there's a whole spectrum of flexibility here, which is governed by the Shore a hardness scale.
Right.
We are usually talking about 95A, which is the hardest variant. It feels a bit like a skateboard wheel. It bends, but it fights you.
It has some stiffness to it.
Yeah. Then you step down to 85A, which is medium flexibility, perfect for vibration dampers. And then you get to the wild stuff.
The really soft stuff.
Yeah. 75A or softer. That feels like a gel shoe insert or like a wet rubber band.
And the mechanical properties of those ultra-soft materials are incredible for shock absorption. They have astonishing layer adhesion because the polyurethane bonds so aggressively to itself.
It is basically indestructible once it is printed.
It is. But those exact same mechanical properties, like that elasticity and tackiness, make them an absolute nightmare to push through a standard 3D printer.
Okay, I'm going to play devil's advocate for a second here because I definitely tried this early on.
We all did.
Right, can't I just run soft 75 a TPU through a standard, affordable Bowden setup if I really take my time? Like, if I tweak my retraction settings and print at a crawl, surely I can force it to work without buying a new direct drive printer?
It is a valiant effort, but it is a battle against fundamental physics. And, well, physics always wins.
Unfortunate, but true.
A Bowden setup is physically incapable of reliably feeding highly elastic material. Think about how a Bowden system is constructed.
Right.
The heavy extruder motor and the driving gears are mounted all the way back on the frame of the printer to keep the print head light.
Yeah, so those gears have to bite into the filament and push it through a long PTFE tube, which is essentially a plastic straw, all the way to the moving hot end.
Exactly. So you have got this massive 40-centimeter distance between where the pushing happens and where the melting actually happens.
It's a long way to go.
It is. Now imagine trying to push a wet noodle through a drinking straw.
Oh, that is a great analogy.
Right. The pushing force applied by those gears transfers onto that highly elastic 75A TPU. But because the material is soft, it does not just move forward. It compresses.
It buckles.
Yes, it buckles and expands outward against the inner walls of the PTFE tube. The friction inside that tube increases exponentially the harder you push.
Until it just binds up entirely.
Yep. Or it just squirts out the side of the gears at the motor and wraps around the driving axle like a bird's nest.
Which is just the worst to clean up.
A direct drive extruder, where the feeding gears sit mere millimeters above the melting zone, is simply non-negotiable for serious TPU work. There is just no room for the filament to buckle.
That wet noodle analogy is painfully accurate. I mean, I have spent hours picking jammed, stretched out TPU out of extruder gears with a pair of surgical tweezers.
It is miserable.
It really is. So if we accept that we absolutely need a direct drive extruder for flexibles, what else changes when we transition away from rigid plastics?
The biggest shock for intermediate users is the extreme speed penalty.
Oh yeah, you have to slow way down.
You might be used to blasting standard PLA at 300 millimeters per second on a modern Core XY machine and watching it lay down perfect lines. But TPU requires immense patience.
How slow are we talking?
I generally have to drop all the way down to 20 to 40 millimeters per second.
That is a massive reduction. I always assumed you had to print slow just to prevent the gears from grinding, to stop that buckling we just talked about.
That is part of it, but it is primarily about volumetric flow rate and the specific thermal conductivity of polyurethane.
Okay, break that down for me.
TPU is highly viscous when melted. It takes significantly more time to absorb heat in the hot end compared to PLA, and it resists flowing out of the tiny nozzle orifice.
So if you try to push it too fast, you outrun the heater block.
Exactly. The core of the filament has not melted yet. Pressure builds up massively in the nozzle, and you experience severe underextrusion.
Which gives you those weak, spongy prints where the layers are not bonded together properly. They just pull apart like string cheese.
Precisely. The melt pool dynamics are totally different. And that brings us to the other critical adjustment, which is retraction.
Right.
Retraction is when the printer pulls the filament back slightly to relieve nozzle pressure, preventing stringing, when the print head moves across empty space.
Yeah, with rigid materials like PETG, you might retract several millimeters.
But with TPU, retraction must drop to an absolute minimum of 0.5 to 1 millimeter.
Because if you pull a highly flexible rubber band backward from one end, it just stretches. It does not actually pull the material up and away from the nozzle opening.
It just thins out inside the melt zone?
Yes, and the consequences of deep retractions on flexible materials are catastrophic.
Completely.
When you pull that semi-melted rubbery plastic up into the cold zone of the heat break, it expands, it cools slightly, swells up, and forms a permanent rubbery plug.
And that is a jam that forces you to completely disassemble the entire tool head.
This totally validates the material first concept. If your application is soft robotics or wearable gaskets, you cannot buy a budget Bowden machine just because it has a nice screen.
You will spend more time unclogging it than printing.
Let's swing to the complete opposite end of the spectrum. We just talked about maximizing flexibility. What if we want maximum functional rigidity? Right now, there is a massive trend toward printing functional parts in PETG loaded with carbon fiber.
It is a fascinating material science development.
Yeah.
The addition of microscopic chopped carbon fibers into a standard PETG matrix is designed to massively increase stiffness and dimensional stability.
Standard PETG is quite strong and has great layer adhesion, but it has a bit of flex.
Right, and it can also creep or deform slowly under sustained heavy loads. When you embed those carbon fibers, they align themselves along the extrusion path as the plastic flows out of the nozzle.
They act like thousands of microscopic internal reinforcement beams.
Exactly.
So practically speaking, when does investing in PETG carbon fiber actually make sense? Because it costs 2 to 3 times as much as a standard spool of PETG.
It is not cheap, no.
Right, and I see people using it to print little decorative statues or desk organizers just because that matte black textured finish looks incredibly cool. The fibers hide the layer lines beautifully. But is that a valid reason to use it?
You are definitely paying a massive premium just for aesthetics if you do that.
Yeah.
The application guide from the source is very clear. Carbon-filled composites are perfect for drone frames, robotic arms, automotive brackets, or anything structural that requires extreme rigidity and low weight.
So for a desk toy, it is overkill.
It is absolute overkill for decorative models.
Mm-hmm.
You are paying for mechanical properties you are not utilizing. And worse, you are wearing down your hardware for no reason.
And that hidden cost is the real kicker. I actually learned this the hard way.
Oh no, what happened?
I printed half a custom drone chassis out of carbon fiber filament and could not figure out why the second half of the print looked like a melted candle with terrible stringing.
Oh, I know where this is going.
Yeah, I took the silicone sock off my hot end, and my standard 0.4 millimeter brass nozzle had a hole the size of a crater.
Yep.
I did not realize it was basically extruding liquid sandpaper.
Yeah.
You absolutely must use a hardened steel or ruby tip nozzle.
It is a rite of passage for intermediate makers, honestly. Brass is the industry standard for nozzles because its thermal conductivity is excellent. It transfers heat into the plastic beautifully.
But it is an incredibly soft metal.
Yes. Those microscopic carbon fibers are exceptionally hard and abrasive. As they are forced under pressure through a tiny orifice, they act like a file.
A literal file.
A brass nozzle will be completely destroyed in just tens of hours of printing.
And the really insidious part is that it does not fail all at once. It is a gradual degradation.
Right.
The abrasion slowly machines the inside of the hole. Your perfectly round 0.4 millimeter nozzle slowly becomes a 0.5 millimeter oval and then a 0.6 millimeter jagged mess.
Exactly. The internal geometry of a quality nozzle is precision machined to control the laminar flow of the plastic.
Yeah.
When that geometry gets gouged out, the physics of your extrusion completely change. You will start seeing horrific stringing, inconsistent line widths, and poor layer adhesion.
And because it happens gradually, you will probably blame your slicer settings or assume the filament is wet, completely missing the fact that your nozzle aperture is destroyed.
So the material first rule strikes again. If you plan to print structural components in carbon fiber, you have to factor a hardened steel nozzle into your initial hardware budget.
And honestly, hardened extruder gears too, since the fibers chew through those as well.
Very true.
So you have bought the right nozzle, you have selected the right material for your application, but your print still fails.
The worst feeling.
This takes us into the really frustrating territory, which is defeating the hidden variables. And the most notorious soul-crushing issue in this hobby is warping, particularly with ABS.
It is the ultimate test of a maker's patience.
Yes.
You see so many people complaining that their ABS prints are warping at the edges, even when they think they have done everything right.
They bought an enclosure, they cleaned the bed, but large prints are still curling up and failing.
It is agonizing.
You are printing a large, flat electronics enclosure. 3 hours in, everything looks flawless. Then you hear this tiny, sharp pop sound from inside the printer.
That sound is haunting.
It is. You look over, and the front left corner of your box has curled up off the bed by 3 millimeters. The dimensional accuracy is ruined. The part is garbage. Why does ABS fight us so aggressively compared to PLA?
It comes down to a concept called the glass transition temperature, combined with a high coefficient of thermal expansion.
Okay, let's unpack that.
Glass transition is the temperature range where polymer transitions from a hard, glassy material into a soft, rubbery state. For ABS, that is right around 105 degrees Celsius.
That's it.
When you extrude ABS at, say, 250 degrees, it is fully expanded. As it cools, it wants to shrink.
Okay, that makes sense.
Now think about the environment inside your printer. The bottom layers of your print are stuck to a heated bed that is running at 110 degrees.
So those bottom layers are sitting right at their glass transition temperature. They are hot, slightly rubbery, and fully expanded.
But as the print gets taller, the upper layers are exposed to the ambient air. Even in an enclosure, that air might only be 35 or 40 degrees.
So the top of the print cools down rapidly, turns completely solid, and starts shrinking violently while the bottom is still hot and expanded.
Exactly. You have created a massive thermal gradient. The contracting upper layers act like a tightening rubber band, pulling upward and inward on the layers below them.
Wow.
That internal stress compounds with every new layer until the upward pulling force literally overpowers the adhesive force holding the bottom of the part to the bed.
That pop you hear is the mechanical failure of that adhesion. The internal stress yanks the corner right off the build plate.
Is pure physics.
So how do we fight that physics? We have to manipulate the thermal environment. You cannot just put a cardboard box over the printer and hope for the best.
No, you definitely cannot.
You need an active or at least heavily insulated chamber sitting at a sustained 35 to 45 degrees Celsius and a bed cranked all the way up to 100 or 110 degrees.
That ambient chamber temperature is the key. By keeping the air surrounding the print at 45 degrees, you slow down the cooling rate of the upper layers. You minimize the extreme temperature delta between the hot bed and the cool top. This allows the polymer chains to relax slightly as they cool, significantly reducing that internal pulling stress.
Drafts are also the absolute enemy here. Even a slight breeze from an open window across the room or an air conditioning vent kicking on can spell disaster if your enclosure is not perfectly sealed.
Yes, because a draft causes rapid localized cooling. If a stream of cool air hits just one corner of your ABS print, that specific corner will contract faster than the rest of the model.
That unequal contraction creates an immediate localized stress point.
Exactly, resulting in a split layer right down the middle of your part, or a severely warped corner exactly where the draft hit.
So we get the thermal environment dialed in. But even with a 45-degree chamber, you still cannot just rely on a clean glass bed. You need chemical adhesion to fight the mechanical stress.
Right. You have to use a PEI bed combined with a specialized adhesive like Majigu or 3D Elasty.
Yeah, PEI, or polyethyramide, is an incredible surface because when heated, its surface energy changes, allowing plastics to grip it tightly. And when it cools, it releases them.
But ABS shrinks with such immense force that it can overpower even PEI.
Right.
A specialized glue stick acts as an interface layer. It creates a chemical bond that holds firmly at 110 degrees, effectively anchoring the plastic to the steel sheet.
And there is a vital geometry rule to add to this. For any flat base over roughly 100 square centimeters, you really need to use a 5 to 10 millimeter brim.
A brim is a thin, single-layer skirt of plastic printed around the perimeter of the object, physically attached to the first layer.
It acts like a massive suction cup.
Exactly. It dramatically increases the surface area in contact with the bed. By doing this, you distribute those internal pulling forces over a much wider area.
If the corner tries to lift, it does not just have to overcome the adhesion of the corner itself. It has to lift the entire 10 millimeter anchor of the brim along with it, which requires significantly more force.
But let's be real. Even with a perfect enclosure, a hotbed, specialized glue, and a massive brim, printing large ABS parts is a constant battle.
It really is.
And there is a highly pragmatic alternative mentioned in the recap. If you are constantly fighting ABS warping, you really should just try ASA instead.
ASA, or acrylonitrile styrene acrylate, is a brilliant chemical evolution. It was originally developed to solve ABS's weakness to ultraviolet light, since ABS turns yellow and brittle when left out in the sun.
ASA is highly UV resistant, making it the king of outdoor functional prints. But its massive secondary benefit for 3D printing is that it has a slightly lower coefficient of thermal expansion.
Which means it shrinks less as it cools.
Exactly. It still requires an enclosure to print reliably, but the internal stresses generated during cooling are noticeably lower.
You get almost identical mechanical strength, better weather resistance, and far fewer curled corners. It is the smart upgrade path for functional parts.
Okay, so let's say you have got your PEI sheet perfectly prepped. Your enclosure is holding a steady 45 degrees. You have switched to AS or PETG, and your print still fails.
Oh, man.
It looks rough, the walls are brittle, and it is covered in stringing. At this point, you want to throw the machine out the window.
Totally.
But the problem is not the environment anymore. The problem is hiding literally inside the plastic itself. We have to talk about moisture.
This is the invisible variable that trips up almost everyone. I have seen seasoned engineers blame their hot end, their slicer, their stepper motors, when the real culprit was simply ambient humidity.
We are talking about hygroscopic materials.
I will be honest, the first time I read that my PETG spool was actively absorbing water from the air, I thought it was a myth invented to sell filament dryers.
A lot of people think that.
Yeah, I live in a relatively dry climate. How much water can a spool of hard plastic really soak up just sitting on a desk?
It is not a myth, it is polymer chemistry. Hygroscopic does not just mean the plastic gets damp on the outside like a wet piece of wood. It means the polymer actively attracts water molecules from the ambient humidity in the air, and those water molecules actually bond with the polymer chains deep inside the filament.
That is wild.
Materials like PETG, nylon, polycarbonate, and the TPU we discussed earlier are highly hygroscopic. Nylon can absorb so much moisture that it becomes unprintable in just 8 hours sitting in a normal room.
Wow. And the symptoms are both visual and acoustic. The dead giveaway is the sound.
Oh yeah, the popping.
When I printed damp PETG for the first time, I kept hearing this tiny, erratic crackling sound coming from the nozzle. It sounded like miniature popcorn popping.
That sound is literally water boiling inside your melt zone. It is a violent physical reaction.
It is exploding.
Yeah. When the water molecules trapped inside the filament hit the 250-degree heat of the nozzle, they instantly flash boil into steam.
That phase change from a liquid to a gas causes rapid expansion. It is basically a series of microscopic explosions right inside the hot end.
And those steam explosions blow chunks out of the extrusion path. The expanding steam forces the plastic out inconsistently.
You get a rough, frosty matte finish instead of a smooth, glossy one.
You get horrendous stringing because the steam pressure pushes plastic out of the nozzle even when the motor is retracting.
And if you snap the part in half and look at the cross-section, you will see it is full of tiny voids where the steam bubbles were trapped.
But the visual defects are not even the worst part. The real danger is chemical.
Okay, how so?
When you heat polymers like PETG or nylon in the presence of water, a chemical reaction called hydrolysis occurs.
Hydrolysis.
The water molecules actually attack and cleave the polymer chains. They break the long chemical bonds into shorter ones.
Oh, wow.
So you are not just getting an ugly part, you are permanently degrading the mechanical strength of the plastic. A damp print will shatter under loads that a dry print would easily handle.
So how do we actually fix it? You have to aggressively dry the filament before printing.
Right.
You can use a dedicated dryer box like a Sunlu S2. You can repurpose a food dehydrator, or you can use a standard kitchen oven set to 50 to 70 degrees Celsius for 4 to 12 hours.
Though I always add a massive warning regarding the kitchen oven method.
Oh, absolutely. Be careful with that.
Standard ovens are notorious for massive temperature swings. You might set the dial to 60 degrees, but the heating element at the bottom might blast radiant heat at 90 degrees just to bring the ambient temp up.
That radiant heat will easily exceed the glass transition temperature of the plastic spool itself, and you will return to find your expensive filament fused into a solid, unspoolable plastic donut.
Dedicated active air dryers or food dehydrators are much safer because they use gentle, continuous convection airflow.
That is a vital safety tip. And the workflow does not end when the timer goes off. You cannot just dry the filament and then leave it mounted on the printer for a week.
Definitely not.
Storing it in a sealed, airtight container with indicating silica gel immediately after drying is mandatory.
Think of silica gel as a chemical sponge that has a higher affinity for moisture than the filament does.
It sucks it right up.
By placing them in a sealed microenvironment together, the desiccant acts as a sacrificial barrier, grabbing any remaining ambient humidity before the polymer can.
This represents a fundamental shift in how you treat your materials. You have to stop treating engineering filaments like standard hardware store supplies and start treating them like perishable goods.
That shift in workflow philosophy brings us perfectly to the next critical phase of advanced printing.
You have dialed in the physical material, you have conquered the thermal environment, you have removed the moisture. Now you need the software intelligence to drive the hardware.
It is a provocative realization that a slicer is not just a translation tool, it is a workflow philosophy. The software dictates the quality far more than the physical hardware does.
This requires a massive shift in perspective for many intermediate users. We tend to view the slicer as a necessary annoyance, a program that just chops our 3D model into flat layers and spits out G-code coordinates.
But the reality is that the printer itself is quite dumb. It just blindly executes motion commands. All the actual intelligence, all the predictive physics of the manufacturing process lives entirely inside the slicer.
The landscape of that software intelligence is dominated by three main philosophies right now.
Yeah.
You have OrcaSlicer, which has emerged as the open source champion for advanced granular calibration. You have Bambu Studio, which offers a highly polished, frictionless experience tied to their specific ecosystem. And you have PrusaSlicer, which is the incredibly robust bedrock of the industry.
If you look closely at their lineage, they all share DNA. PrusaSlicer revolutionized the industry by building an incredibly stable open source foundation with features we take for granted today.
OrcaSlicer is actually a fork of that software tree, but its developers built in highly specialized automated calibration suites.
It is designed for users who want to aggressively tune every microscopic parameter of their machine's kinematics.
Bambu Studio took the opposite route. They used that same core intelligence, but heavily optimized the interface to hide complexity, focusing on automatic spool recognition and cloud integration for a seamless user experience.
This leads to one of the most important realizations for anyone looking to upgrade. It is a bold claim from the source, but the math backs it up.
Spending thousands on upgrading your hot end or snapper motors will give you a significantly smaller boost in print quality than spending one focused hour systematically calibrating a specific material profile in your slicer.
It sounds totally counterintuitive to a hardware enthusiast, but it is an undeniable fact. Hardware upgrades offer rapidly diminishing returns.
A stiffer aluminum frame might reduce some high-speed vibration ringing, but an uncalibrated slicer profile introduces catastrophic foundational errors in the physical dimensions and structural integrity of the part.
I always compare printing without specific material calibration to playing the lottery. Even if you buy 2 spools of black PETG from the exact same premium brand manufactured a month apart, they might have slightly different melting viscosities or a microscopic variance in filament diameter.
If you just slap the spool on and run the generic PETG profile, you are just hoping the math is close enough.
And close enough is completely unacceptable for mechanical parts. Let's look at the actual physics the slicer is trying to calculate, specifically a setting called pressure advance, or linear advance.
Right. And for anyone who has not tuned this yet, pressure advance is basically compensating for the fact that molten plastic acts like a spring inside the hot end. It is not a direct one-to-one movement.
Exactly. We have to think about fluid dynamics. The extruder motor pushes solid cold filament down into the hot end. That solid filament acts like a piston, pushing against the pool of melted plastic in the nozzle.
But molten polymer is a viscous, compressible fluid.
When the motor starts pushing, the plastic does not flow out of the nozzle instantly. Pressure has to build up inside the melt zone first. The spring compresses.
So there is a physical lag between the gear turning and the plastic actually extruding.
Yes. And conversely, when the print head reaches the corner of a square and needs to decelerate, the motor stops pushing. But that high pressure inside the nozzle still exists.
The spring wants to uncoil.
So the molten plastic continues to ooze out for a fraction of a second, even though the motor has stopped. This results in a bulging, ugly blob right at the corner of your print where the tool head slowed down.
So pressure advance is the slicer mathematically predicting that exact springiness.
It calculates the precise lag. It tells the extruder motor to briefly push extra fast right at the start of a line to quickly compress the spring and build pressure.
And crucially, it tells the motor to slightly reverse or stop pushing just before reaching the corner, allowing the residual internal pressure to finish the extrusion perfectly as the print head decelerates.
It is an incredibly complex fluid dynamics prediction happening thousands of times per minute.
And the margins are razor thin. If your pressure advance value is wrong by just 0.01 in the slicer, you get those rounded, sloppy corners.
You absolutely cannot buy a hardware upgrade to fix a bad pressure advance calculation.
You really cannot. And the exact same logic applies to flow rate, or the extrusion multiplier. If your flow rate is off by just 3%, you will suffer ugly overextrusion, particularly visible on top layers and overhangs.
Flow rate is essentially the slicer's core math for volume. It calculates exactly how much plastic needs to be pushed to fill a space.
Yes. The slicer assumes your filament is exactly 1.75 millimeters thick.
But if your specific spool is actually 1.78 millimeters thick, or if the plastic expands slightly more than expected when it transitions from solid to liquid, you end up pushing significantly more volume of material than the slicer intended.
3% does not sound like much, but plastic is incompressible once it cools. Over hundreds of layers, that excess 3% volume has nowhere to go.
It bulges out the sidewalls, it scars the top surfaces as the nozzle plows through it, and on overhangs where there is no underlying support, it just sags heavily.
This is why that hour of calibration is so powerful. You print a flow rate test block, you measure it, you print a pressure advance line test, you find the perfect value.
You save those exact values to a named profile for that specific spool, and suddenly your budget printer is outperforming a premium machine that is running blind on default settings. You are removing the hidden variables.
So we understand the software intelligence. Let's bring this back into the physical world and talk about hardware ecosystems. This is where the industry is fracturing into two distinct philosophies.
We are looking at the battle between open versus closed ecosystems and what that means for your workshop long term.
It is the most significant philosophical divide in the desktop manufacturing space today.
On one side, you have Bambu Lab, which has aggressively championed the closed, frictionless ecosystem. Their entire pitch is just print.
They control the hardware, they write the proprietary firmware, they maintain the slicer, and their branded filament spools have RFID tags that auto-configure the settings.
They are basically the Apple of 3D printing. It is the iOS approach.
That is the perfect analogy. And on the other side, you have companies like Prusa representing the traditional open hardware philosophy.
The firmware is open source, the hardware designs are public, third-party modifications are highly encouraged, and the community constantly develops new upgrades.
And then, of course, you have brands like Anycubic or Creality offering incredibly capable, highly modifiable entry-level machines for very little money.
This ecosystem choice dictates your long-term relationship with the machine. Are you comfortable with vendor lock-in if it guarantees a frictionless start? Or do you demand the freedom to run third-party upgrades and repair your own machine 5 years from now?
Because vendor lock-in is not necessarily a bad thing if reliability is your only goal. I mean, I accept iOS on my phone because I just want it to work without compiling a kernel.
Exactly. A closed system dramatically lowers the barrier to entry, but you are entirely at the mercy of the manufacturer.
If a cloud service goes down, or if the company decides to stop supporting a specific feature in the future, you cannot install custom firmware to bypass their restrictions. You are locked in.
An open system, like a Prusa, requires more initial technical curiosity, but the reward is true ownership. You can completely rebuild and evolve the machine over a decade.
Let's look at a very specific buying decision within that closed ecosystem that comes from the Q&A. If someone has decided they want that frictionless experience, how do they choose? Should a serious hobbyist buy the Bambu Lab X1C or the newer industrial-focused H2S?
It comes down to a classic production engineering calculation, which is throughput versus redundancy. The X1C is an incredibly capable machine. It covers almost every hobbyist need with an active chamber and a great build volume.
The H2S is designed for sustained, high-speed industrial batch production.
But the insight here from the community is fascinating. For the price of one single H2S, you could just buy two X1C units. Which is better?
For almost anyone outside of a massive factory floor, two X1C units is the far smarter move. Think about machine downtime.
If you buy one expensive, fast H2S and the thermistor wire breaks, or the hot end suffers a catastrophic blob failure, your entire production capacity is instantly reduced to zero.
You are dead in the water while waiting for parts.
If you buy two X1Cs, you have doubled your concurrent throughput. You can print two different jobs simultaneously.
And crucially, if one machine suffers a failure, you are still operating at 50% capacity. Redundancy beats single machine speed every time.
That is an incredibly practical way to view hardware investment. Now, let's tackle the defining feature of these modern closed ecosystems, which is multi-material systems, specifically the Bambu AMS.
Being able to print in 4 colors automatically feels like magic, but does it really work for everything? People always want to know if they can run third-party filaments through it.
The answer is a heavily qualified yes. The AMS is a mechanical marvel, and it works wonderfully for standard, rigid 1.75 millimeter materials. Yeah. PLA, standard PETG, ABS. As long as the physical cardboard or plastic spool fits inside the unit and is not warped, it will feed just fine.
However, there is a massive warning label here. There are specific materials you should never, ever load into an AMS unit.
Right. You absolutely must never load soft TPU below 95A, incredibly damp nylon, or heavily abrasive carbon fiber composites into an automated material switcher.
Let's go back to the physics we discussed with the Bowden tubes. The AMS is essentially the most complicated Bowden system ever designed.
It relies on internal feeding gears, complex plastic funnels, and incredibly long routed PTFE tubes to shuttle the filament back and forth between the spool and the printer head during color changes.
And that intricate routing is exactly why it fails catastrophically with specialized materials.
If you try to command the AMS to quickly push and pull highly elastic 85A TPU. Through those winding tubes, the rubbery filament compresses, binds up, and jams the entire internal mechanism.
You will not be printing. You will be spending 3 hours disassembling the AMS block to fish out stretched-out polyurethane.
And what about the carbon fiber? We know it eats brass nozzles, but what does it do to the AMS internals?
It is an abrasive nightmare. During a multicolor print, the filament is rapidly pushed back and forth thousands of times. Those microscopic carbon fibers will literally saw through the internal plastic funnels and shred the inside of the PTFE tubes.
The system will degrade incredibly quickly, introducing massive friction to all your future prints. For abrasives and flexibles, you must bypass the AMS entirely and feed the spool directly into the printer's extruder.
We have covered an immense amount of ground today. We have dissected the fluid dynamics of flexible polymers, the destructive abrasion of carbon composites, the thermal tug-of-war of ABS warping, the chemical reality of hydrolysis, the predictive math of slicer calibration, and the philosophical divide of hardware ecosystems. It is a lot to process.
It is deeply technical, but it all builds toward a single, cohesive philosophy for mastering this technology.
And that brings us to the single most important moment of our deep dive. We have analyzed the problems, we have broken down the physics, but if you take away only one single actionable concept from this entire discussion to apply to your workshop today, we want it to be this.
We call this philosophy systematic iteration over hardware chasing.
Let's break that down with a real-world scenario. You're printing a precise mechanical gear. The print finishes, and the top layer looks terrible. It is rough, scarred, and the nozzle has dragged deep trenches through the plastic.
The beginner's instinct, which is the trap of hardware chasing, is to immediately think, my hot end is not precise enough. I need to buy a high-flow nozzle, or I need to order a completely new printer.
Hardware chasing is trying to buy your way out of a physics problem. Systematic iteration is acting like an engineer. It requires strict discipline.
Instead of throwing money at the machine or randomly downloading 5 different profiles from Reddit hoping one works, you establish a rigid baseline.
You use one single type of material, just standard PLA. You use one standard 0.4 millimeter nozzle, and you use one single default slicer profile. You do not change anything else.
You examine the failed gear. You isolate the specific visual defect. In this case, rough, scarred top layers almost universally indicate overextrusion. The nozzle is plowing through excess plastic.
You identify the single variable responsible for that, which is flow rate. You go into your slicer, and you reduce the flow rate by exactly 2%.
Nothing else. You do not tweak the temperature. You do not mess with the cooling fan. You do not change the print speed. You only change the flow rate.
You print the gear again under identical conditions. You examine the new top layer. Is the scarring completely gone? Is it slightly better but still visible?
If it's better but not perfect, you reduce it by another 1%. You iterate.
Yeah.
The profound lesson here is that the sum of 10 small, documented, systematic calibration steps will dramatically outperform throwing a hardware upgrade at an uncalibrated machine.
You are training your own brain to understand the variables rather than hoping the hardware magically fixes them for you. It is an incredibly empowering mindset. You stop being a victim of unpredictable machine failures, and you become the operator commanding the process.
As we look forward and summarize our journey today, we have moved from the physical constraints of material properties, like understanding exactly why soft rubber buckles in a tube, all the way up to high-level ecosystem choices that will dictate your workflow for years.
We have seen that the most valuable innovation is not always in a flashy marketing brochure. It is in the community. It is the open source developers refining the math in OrcaSlicer and the makers figuring out the exact chamber temperature needed to stop ABS from ripping itself apart.
And as we consider where desktop manufacturing goes next, we are left with a truly provocative engineering question.
What is that?
We are moving rapidly toward advanced multi-material prints becoming the standard expectation. But the current closed ecosystem paradigm, like the single nozzle AMS, relies on generating massive amounts of purge waste.
Every single time the printer changes color, it has to mechanically flush the old melted plastic out into a waste bin to clear the nozzle.
Which is financially annoying when you're purging $2 a kilo PLA, but it is completely unsustainable when you are flushing $50 a kilo carbon fiber nylon down the chute.
Exactly. So the ultimate question for the industry is this. Will the future continue down this path of single nozzle systems that waste immense amounts of material just to maintain mechanical simplicity?
Or will we see a massive pivot back to multiple independent extruders, like the tool-changing systems we see on the Prusa XL, where each material has its own nozzle, completely eliminating purge waste despite the much higher initial cost of the hardware.
It is the ultimate engineering trade-off between machine complexity and material efficiency. Watching how the market and the community settle that battle over the next few years is going to be fascinating.
Sure.
For the full numbers, see printera33d.com. Thank you for joining us on this deep dive. The next time you load a fresh spool, hit print, and walk away, we hope you do it with the confidence of someone who actually understands the physics happening inside that melt zone. Keep iterating, keep questioning the hidden variables, and we will see you on the next deep dive.